The engineering problem we investigated was designing a system that can convey grain upwards into a grain rail terminal silo. Conveying grain requires significant energy due to the heights involved and the mass lifted upwards. At least 25 gigawatt hours are spent each year in Canada for conveying grain upwards into silos. Inefficiencies affect farmers, terminal operators, and consumers through higher operating and maintenance costs. Pneumatic conveying of solid material involves flowing air with granular material to move it from point A to point B. At low solid air flow ratios, dispersed flow occurs when the solid's particles are suspended in the air. This is the common flow regime for grain transport applications. At high solid air flow ratios, dense phase flow occurs, where the solids are pushed by the air in slugs. The motivation for this engineering project is to evaluate the feasibility of a dense phase system for silo loading.
The process starts by pouring wheat into a container known as a hopper. This hopper is connected to a rotary feeder which steadily measures the grain and moves it forward. Air is drawn in first through a filter which protects the compressor or blower by removing dust and debris. This clean, compressed air is then used to push the wheat through a series of pipes, delivering it all the way up into the storage silo. As the silo fills with grain, it releases dust into the air. A filter is attached to the silo to collect this dust, which lowers the risk of dust fires. To evaluate our design, we begin by calculating the required airflow and pressure using established engineering equations, validated through computer simulation. Beyond technical performance, we also analyze energy efficiency, upfront costs, and annual operating expenses. Finally, we prioritize workplace safety by addressing the risk of dust explosions, including an analysis of potential heat generation. What are the anticipated benefits? Our analysis leans towards the dense phase conveying system. The main advantage is how it works. It moves more grain using less air. This allows us to use smaller pipes, which directly lowers our initial equipment and installation costs. But the more significant benefit is long-term efficiency. The dense phase system simply uses less energy to do the same job. This leads to substantial lower power consumption year after year, which means major savings on our annual operating expenses. In conclusion, choosing the dense phase system positions us for lower upfront investment and significantly reduced long-term energy costs.